Section 8. Course Review and Unfolding Trajectories. Video 1. Reviewing our apps. In the previous section we completed the third app of our course. In this section we will briefly review all three of our experiments with AR frameworks and explore further possibilities of this medium. We will touch upon a separate dimension of computer vision and consider sustainable ways of utilizing the technologies as they fully enter the consumer market. Let's start from the Virtual Assistant app, for developing of which we used AR Foundation. It was an introduction to the core functionalities of the API, available for both Android and iOS. The app enabled instantiating and controlling a monster assistant in the space, streaming audio from URL and delivering voice commands to manage playback. There is a range of issues that could be improved in the app. Most of them are a result of using the speech-to-text plugin, which demands more time for careful implementation and platform-dependent testing. Some of the Android devices require manually setting the permissions in the settings, which is inconvenient. We could request permission at the launch of the app if it has not been given or the request window did not show up automatically. The plugin we used connects to respective OS's native speech-to-text systems. Another challenge of the functionality we implemented comes from the fact that the microphone on Android picking up the audio that the assistant is delivering, which can distort our voice commands. iOS by default puts the audio on mute when the user is delivering a command. The same approach could be reproduced for Android by pausing audio source or the audio listener within voice commands coroutine in voice navigation. Another little spot we left for bugs to breed in is when the user touches the screen and the assistant is headed towards a new destination. We decided to set up the assistant to listen for voice command while moving, but if we send the assistant on short journeys and repeatedly touch the screen, it might lead to a glitch in the voice recognition process. Rather than implementing further conditions into voice navigation script, which would work, you could also create a separate button responsible for listening, for instance when the touch phase is pressed and stationary. This would mean separating movement from listening for voice commands. Last little issue that we haven't patched is that the assistant carries on moving its jaw even if the audio stops playing. We need to bulletproof our is-speaking boolean, which keeps on triggering the jaw movement coroutine in our assistant speak script. What else bothers you about our first app? It's a good practice to come up with as many issues that can be improved on as possible, and we could definitely spend more time on this prototype. Same goes for the next two. Okay, let's move to the second app now. In the section 4 and 5, we developed a multiplayer urban design app, which enabled players to instantiate building modules on a platform and manipulate them in real time. Cloud anchors, in combination with UNet, enabled us to deliver the range of functionality. Of course, the first issue we might think of is the fact that High-Level API, HLAPI, is depreciated in Unity 2019. We do not need to worry about it though, because UNet HLAPI will be supported for quite a long time still in Unity 2018. Of course, you can replace UNet functionalities with a different system such as Photon, and there are discussions on Unity forums that could help you implement it. Let's focus on what can be improved within the existing app. As we hinted, when developing the touch interface, you can make it more sophisticated on your own or use existing solutions such as Object Manipulation Framework included in recent releases of AR Core. It's particularly relevant for rotation functionality we barely sketched out, but could be useful for further features you might want to include, such as scaling. Try AR Core Object Manipulation Sample App if you haven't already. One of the slightly inconvenient issues when operating on the objects is lack of intuitive feedback spread across the user's devices. This could be improved, for instance, by highlighting the object that is currently operated on by another player. Depending on what are your modules, you could approach it from different angles, for instance, by applying a shader with outline or activate a little object under or on top of the module when someone interacts with it. Furthering this aspect of making collaboration smoother, we could consider locking objects when a user is manipulating them. Let's compare it to an update lock in SQL database. Everyone can read what is happening to an object, but only one person can alter the state of an object at one time. I want to highlight another useful feedback mechanism. We haven't touched upon haptic feedback, and that could be a good signal to receive whenever someone deletes an object. We might be focusing on one part of the board while other players would delete objects we cannot see disappearing. There's of course a lot of potential for audio cues too. Let's now look at the app we created over the last two sections, which is AR mesh generation and customization in VR mode. Firstly, we would recommend further exploring bespoke mesh generation we uncovered at the beginning of the previous section. Ultimately, it gives you more independence regarding how you want to develop user journey. You can still connect yourself to AR Foundation Plane subsystem. We encourage you to study the scripts we highlighted and develop your own functionalities on top of them. One of the practical choices, given the time constraints we had to make, was mixing 2D and 3D raycasts by applying colliders on our UI elements. It led to occasional difficulties with handling plane selection, particularly when they have not synced at the time of looking at them. It could be addressed by clearly separating 2D UI raycasts with 3D ones. It could be done by assigning appropriate layer masks, which would require rewriting our scripts but might end up reaping very reliable results. Passing relevant masks in our raycast if conditions would then boost the efficiency of our prototype approach. There are a couple of issues with the light estimation. In the current setting, it might make sense to have a little indicator providing us feedback regarding the light source having been placed. It could be a UI element to also depict the location, since they do not interact with light, alternatively text or audio message delivered to the user. As mentioned towards the end of the previous section, it would be optimal to devise a method of manipulating the light levels directly through material properties, rather than repositioning directional light. Here we recommend inspecting AR core shaders in order to develop ones you might need. Another obvious issue has to do with hard coding the timing for light placing button. Different people take varying amounts of time to put on a headset. Perhaps it might be worth creating an intro for users where they see nothing except the start button, which launches the actual experience. One of the merciless issues with AR in VR mode is that everything appears closer than it is in reality. It is a question of field of view, which you can attempt to tweak on Unity Camera Object in hierarchy, but the SDKs override the manual settings, so it's difficult to navigate the issue. Another aspect independent from us is the imperfectness of AR Foundation, AR cores and AR kits for that matter scanning abilities. Consistent remeshing real environment is very tricky, and it is most likely to perform well only in simple environments. Another challenge lies in the fact that VR is separated, visible only to the user, hence it would make sense to do screen capture or even implement cloud anchors so users can collaborate. Think of all the modules we developed in the course as interchangeable elements you could apply to all our several apps, speech to text being a perfect example.